Okay, welcome back everybody. This example looks like one that we've done before, and it is actually one that we've done before, but we did that in the context of forces and Newton's third law. This is going to be using the context of momentum and forces applied over a certain amount of time. So let's just go ahead and jump right into this and try to make some sense out of it. So the first thing I'm going to do is I'm going to shrink this down a little bit. Well, let's read it first and then I'll shrink it down. Two groups of canoeists meet in the middle of the lake. All right, so they're meeting here, not doing anything. They're just talking. And then after they're done talking, there is a push that exists between them. One person pushes off. We call this the force from him on canoe 2. But while he's pushing, he also feels a push back from canoe 2. And that's the force on that he and canoe 1 is going to be feeling. So both canoes feel the same force, 46 newtons. Canoe mass 1 and its passenger occupants, it should be and its occupants, is 130 kilograms. Mass of canoe 2 is 250 kilograms. We want to find the momentum of each canoe after 1.2 seconds of pushing. All right. So I think in the previous time we did this, we used, I think we found the final velocity or something like that, or the acceleration maybe, but we're going to find the momentum right here. So I'm going to resize this a little bit. All right, so we can write down everything that we know on the left. Okay. Mass 1 equals 130 kilograms, and mass of canoe 2 equals 250 kilograms. All right. The force applied. And you know what? I'm going to write that below here. The force on, let's see, on canoe 2, from 1 to 2 you might say, is 46 newtons. And keep in mind we're calling this direction towards the right positive, which means that the force on canoe 1, the pushback from canoe 2 on canoe 1, is going to be negative 46 newtons. Right, so that's going to make all the difference right here. This push, this two-way push, from 1 to 2 and from 2 to 1 is going to be an internal force. It's going to be an internal pair of forces. And it's going to affect the outcome here. And the final time is 1.2 seconds. All right, T or delta T equals 1.2 seconds. All right, it's asking us to find the momentum of each canoe. All right, this canoe 2 is obviously going to be going that way, and canoe 1 is going to be going this way. But what is the actual final momentum? If you have a final momentum, you have an initial momentum. All right, what's the initial momentum of these canoes? Well, they're just sitting there, right? They're not doing anything at all. So the momentum for 1 is going to be 0 kilogram meters per second, as is momentum 2, 0 kilogram meters per second. All right, that should enable us to help. That should help enable us to find the final momentum of each canoe. All right. Well, let's just start with canoe 1. All right. For canoe 1 right here, the initial momentum is 0. Momentum final is what we want to know right here. The force that one feels, that canoe 1 feels, I should say, is negative 46 newtons, and it is applied over 1.2 seconds. Oh, I didn't label that, did I? T equals 1.2 seconds worth of pushing. Okay, 1.20 seconds, I should say. Fix that. All right. 20 seconds. There we go. All right. Well, the momentum change. The change in momentum is force times time. Right? Both of those are equal to impulse, and so the change in momentum is equal to impulse, has a force times time, so they're equal to each other. So we can say momentum final minus momentum initial equals force times time. And we should be able to solve for our final momentum. You could say we can add the initial momentum over here, but it's going to be 0 anyway. So our final momentum final is simply going to be force times time. But keep in mind your the direction of your forces. It's going to be negative 46 newtons times 1.20 seconds. So our final momentum of canoe 1 is going to be 46 Oh, I'm not doing this right. 46, 1.2. Negative 55.2 meters. Oh, meters, what are we doing? Well, I guess you could call it, well, no, it's not going to be meters. It's going to be our units of momentum, right? It's mass times velocity, kilogram meters per second. Kilogram meters per second. That is our momentum. All right? So the mass really did not have anything to do with it, with the momentum change. All right? We're going to find the same thing is true for canoe 2. For canoe 2, well, the initial velocity, the initial momentum is 0, right? The final momentum is what we want to solve for. The force that is being applied equals now 46 newtons, and the time is going to be the same amount of time, 1.20 seconds. What's the only difference right here? Well, this is going to be the same math over here as it is right here, but our final momentum, P final, force times time, is going to be positive, right? It's going to be 46 newtons times 1.20 seconds. And that's going to be 55.2 kilogram meters per second. That's our units for momentum. Okay, so they have the same momentum. What's going to be different about them? What's going to be different here? So the same push, but different masses right here. They have the same momentum, but they have different speeds, right? For the same amount of push, or the same force applied between the two canoes, this 46 Newton force is going to make these two guys shoot away a lot faster than this canoe full of people over here. But the momentum is the same. The momentum is the same. So what's the momentum of the system? The whole system right here. Well, the momentum of the system is the same as it was at the outset. What's the initial momentum of the system right here? Initially, well, 0, right? 0 plus 0 is 0. What's the final momentum of the system? It's still 0, because canoe 1 has negative 55.2 kilogram meters per second of momentum, and canoe 2 has 55.2. They balance out to 0. So this is what we're talking about. Even though there is an internal force between the two canoes, it can be a push, a contact force, or it can even be a pull between a rope, the two ends of a rope. Let's say you wanted to have a tug of war between two canoes. It wouldn't matter, because the whole system, while each part of the system is feeling a different force, the whole system is experiencing the same momentum, because all the momenta parts of the system are going to be adding up. All right, so I'm going to stop this one right here, but I'm going to continue it in the next video segment and talk about if momentum is conserved, and I kind of have touched on that a little bit right now, but and if energy is conserved and other things. So we're going to kind of expand on that next segment, so I'll see you then.